Hello everyone, welcome to Deriving Rotational Inertia for Common Objects. In this video, I will show one proof on solving the rotational inertia for a solid cylinder, and then we will see how that goes. So let's get started, everyone. So what is rotational inertia? And so rotational inertia is really just kind of like a rotational mass. And it is defined as I is equal to the summation of the ith particle for n particles, like this. And basically what this means is that essentially what makes the rotational mass different from the normal mass is that the normal mass just has a mass m, well, duh, kind of thing. But rotational inertia with the symbol I is defined like this. And the reason why it's so is because when you rotate, rotational inertia kind of explains how difficult or how much resistance does the mass has to rotating. And so the reason why we have an R here is because the distribution of mass matters when you rotate. And so therefore, today I would like to talk about how can we find rotational inertia for various items in mass. So let's talk about a special object, a solid cylinder. And I'm going to rotate it around the z-axis. And today I would like to solve the rotational inertia for a solid cylinder using single variable calculus. Alright, so let's get started. But before I start, I first need to talk about how do we do this for a rigid object. Well, it turns out that if each mass has a very small mass and we sum it infinite times, then it turns out that we could just get the limit as m approaches 0, or mi, I suppose, of the summation, then it essentially becomes an integral of r squared dm. Which is, I guess, really interesting. But in practice, though, this dm is not really used directly to integrate, like i.e. we don't integrate from, like, say, mass 0 to mass m, because that's kind of impractical. And so therefore, we usually use the fact that some density is equal to the mass divided by volume, whether it be at length, area, volume, or even 40 volume, depending on scenario. But so basically we will use this to our advantage. So let's see how we can solve this for this solid cylinder respectively. And so first, that we might use a surface density. So surface density is equal to the mass divided by its area, and therefore we get dm dA. And the reason why we can do this is because we assume that this object is uniform. And so therefore it works because it's constant. So therefore, so the density of the entire object is equal to the density of each small particle. And we use this part and this part to convert, where dm is equal to the surface density times dA. And we know that this is equal to the mass divided by area, so mass divided by area dA. And so now let's talk about how to actually integrate this. So here's how we will do it. Imagine you looked from the top, so then you will look at this projected onto the xy plane. Then really it just looks like a circle if you look at it from above. And then what we can do is that we can integrate each ring. And if we can integrate the ring from r equals 0 all the way up to the radius r, and let me say that this object has radius r, mass m, and length l. Then we can integrate this and find the answer. So first, let's make some adjustments, and just keep in mind that r is the distance from the axis. Cool. And so first, let's fix this. So let's rewrite the I as the integral of r squared dm, and change this to the integral of r squared sigma dA, as I showed you above. And of course, we know that sigma is equal to mass divided by area, but we know that the area of this circle, or because we're at the cross section here, is equal to the mass divided by pi r squared. Then what we need to do is figure out how to rewrite this. And so we know that dA is the area between radius r and r plus dr. Because you can kind of see that we're interested in this cross-sectional area. And if we could just somehow sum this into an integral, then we can find the answer if we integrate from r equals 0 to r equals r. Cool. And so therefore, we know that the area between here is equal to the difference in the area of the outer circle minus the inner circle. And hence we can do some simplification. And we can see that the r's cancel, or r squares cancel. Now here's the trick. We actually eliminate this. The reason is because if we integrate it, then we know that the dr has a limit as it approaches to 0. Well, if that's the case, then imagine what dr times dr is. If this thing is already approaching 0, then this times this is much, much smaller than dr. So hence, we could pretty much just assume that dr squared is 0. And so therefore, we can rewrite this as 2 pi r dr. Nice, and that's what dA is. And so if we go back to here, then we can rewrite the integral as I is equal to the mass divided by the area, right? Because that's the sigma here. And the area, as we know, is pi r squared. And we integrate r squared, right? Because this is the distance, because it is the distance from this axis. And imagine like there's infinite particles, I guess. And that's the distance from the axis of r squared, and dA was 2 pi r dr, and we go from r equals 0 to r equals r, and then we can see that the pi's go away, and these r's combine, and the 2 can be taken out as a constant, so we got 2m over r squared, the integral from 0 to r cubed dr. And then we get 2m over r squared times r fourth over 4, taking by the antiderivative from 0 to r. Evaluating, we get great, and then that is essentially our rotational inertia for this cylinder. And in my PDF, I have written a PDF on a single variable one. And the rotational inertia for the single variable version of the PDF has a lot of shapes. And it's not just cylinders. We will also talk about spheres, cones, and even a rod. A thin rod to be exact. And later, I will also submit a multivariable version of it. And here I will talk in much more detail on how to solve the rotational inertia for various shapes. And the reason why I'm not doing as much for single variable calculus is not because it's too much or anything like that, but rather the derivations are kind of super technical for a single variable because it requires a lot of creativity. So therefore, I will just not talk about it because it would just be way too long to even type it all in. And so therefore, I would like all of you to check it out. And yeah, and I think that's it for today. And hopefully you found this video very interesting. Please like and subscribe, and enjoy a nice day, everyone. See you in the next video. Bye.